I'm not going to sell this.
Okay.
Oh no, I'm not going to sell this. I'm just going to
Present the idea.
yeah. That,
You ready to start?
yeah, I'm ready to start.
Hey, good morning, canard enthusiasts. We're going to kick it off, and I'd just like to ask that everybody, we just have one conversation. You know, if you want to have your side conversations, that's great, but kind of separate from the group. Turn it over to Klaus.
All right. Well, here we are. Thanks for coming. And I wanted you all to come to tell me what I can do to make this go any faster. Any suggestions?
Can you
Tell us what you know.
ignition the same way yours is?
I'm sorry?
Can you tune my ignition, tune it the same way yours is?
I sure can.
Okay.
For an extra six pack or so. So with the engine doesn't have that high a compression ratio. It's 10-1. It's the physical compression ratio, but it's not the compression ratio that matters. It is the BMEP, the brake mean effective pressure, and that is a resultant. For example, you can have a large valve overlap, then and 13-1 compression, and the BMEP is the same as that with less valve overlap at 10-1. And the same thing if you have a tuned intake system, you actually ram more air into the cylinder, and that increases the BMEP. So I've analyzed the waveforms with this very custom intake system, and I'm getting the equivalent of 32 to 33 inches on a 29-inch day. So that the ram tuning works like a supercharger, and that of course raises the BMEP, and even to something above what the 10-1 would normally produce, and that does require a slightly different timing curve. So once you get your intake system ready, Gil will help you out. So.
Change your ring gap to accommodate the expected higher. You've got the 10-1 compression, but you also have a supercharger like.
So I have what? The supercharger.
Well,
ring.
It's not a supercharger, but
the supercharger effect.
Effect, yeah. So you're putting more air.
Yeah.
Mixture in.
So this is a question about ring gap changes, and the ring gap is not affected by the BMEP.
Okay.
So you don't change that. You don't want any gap. But it's interesting from experiments that when you have worn out rings, at high speed it makes absolutely no difference. It's amazing. At high speed you practically don't need rings. Can't get the engine started, but
Well, once it starts.
But yeah, once it starts, well, you will notice a decrease as your rings wear and you have more and more blow by. You will notice a decrease in climb and acceleration. So at low RPM, you notice a difference. At high RPM, there doesn't seem to be enough time to have any significant leakage or have an effect of the leakage. But to get way ahead of that, those guys that have been following the Cobra forum, long time ago I've been using crankcase pressure monitored on the Garmin. So I monitor the crankcase pressure live and have it alarmed. And it's interesting to see it's actually fairly unstable at times, and it bounces way up and then goes way down and then comes back up. And when it's up, that means one of the rings is sticking a little bit, one or more. And at that point, because of the high BMEP, I have to throttle back because it can detonate. Once the rings stick, you get oil into the combustion chamber, and the oil has a very low octane rating, so that promotes knock, and I have to be careful because it's really a high BMEP engine due to the tuning and the combination of valve overlap and the compression ratio.
Hey Klaus.
Yeah.
On your pressure transmitter, can you remember the brand and
No.
approximately the pressure
Nope.
range? Okay.
Don't remember that.
Shucks. I don't know what to select.
Do you have
I have a breather separator, and if you look on there's a little hole on the bottom of the cowling on the right side. That's where it exits, and that breather is positioned so that I get slightly negative flow. So that's actually a change over last year. The bottom cowl is new and 5 pounds lighter, and the hole is one size bigger. Last year I had a 1/2 inch hole, and it was about 0.1 kilopascals pressure on average, positive, between 0 and 0.1. Now it's between 0 and 0.2 negative, just from that increase to 5/8. So for my engine, that seems to be the right size. So obviously, if you have an average negative pressure, you won't have any oil leaks.
So maybe 1 Pascal would be a good range for
1
the pressure?
Pascal is not very much. 1 kilopascal.
Would that be all right for the span of the pressure transmitter? Pressure range?
You know, I really don't remember.
Okay.
But mine seems to go to like 0.3 kilopascals.
Okay.
So that's 300 pascals, right? Plus minus 300 maybe.
Okay.
Maybe plus minus 1/2 kilopascal.
Okay.
Something like that, which should work.
That's close enough. Thanks.
Yeah. Well, it depends on how tight your engine is set up. And but once you have 1 kilopascal positive crankcase pressure, then you don't need to measure it.
Okay.
You know, you don't want to be horrified. So
you said you put a new bottom on here. I noticed your knacker was a little bit different. You don't have a straight fence on your leading edge. Is
Yeah.
that a change also?
that change I made about 30 years ago on the Very Easy already. And the other difference is that this NASA duct has a diffuser in the back, about a 1 foot radius, and it has a radius in the upper corner. And that is very important. It significantly improves the flow of that duct. And I gave my molds to Aero Composites, and they can make parts. They have a mold for the Very Easy duct as well as for the Long Easy duct. And because of all those features, I highly recommend that you get that. And then, you know, that's a part that we know is pretty right. And then if you have the urge to tinker with the airplane more, do something different that you can't buy. You know, I'm always frustrated to see people make their own wheel pans while they can buy one. You know, you can do things like this, like straighten that angle out on the aileron. You know, so that the gap is in line with the flow rather than 30 degrees to the flow. Or work on that fillet between the wing and the winglet. Those are things you can't buy. So those are the things you want to do in your shop by yourself. So it seems silly to have parts that are so well proven available and then make your own. So then the NACA duct, you can tune it or adjust it by moving the inlet lip fore and aft. So mine is tuned to have, right now, that this airplane, while I still have large CHT deltas, the temperatures are perfect for the flight condition that I like to fly at, and that's 17.5, wide open throttle, leaned a lot. And at that point in the summer, like now, we were seeing the highest temperature was 356 on the cylinder temperature. Oil temperature was 180. That is perfect. The problem is when I then go down to a race at Wausau, things get a little dicey. So then I have to manage that a little bit.
What was your cylinder temperature?
At the race or at the altitude? 356 was the highest, and 2 of them are below 300.
And when racing?
You had to ask that? I let it go to 430 on the hottest, and I think it was 230, 228 on the oil. So then I started riching it up just a little bit, pulled the timing back just a little bit, and those are okay temperatures for an hour and a half. You know, there's nothing wrong with that. So, but that's how you adjust the NACA duct. And those ears that are on there on the leading edge are to get a little turbulence that goes more towards the center in there, because the flow comes down the fuselage and rotates into the duct. So then you can see the intake is rather large. The intake, the throttle here is bigger than the throttle on a Lycoming 580. I don't know what they're thinking, but I can, when I'm at altitude and I throttle back, I have about, I don't know, half an inch where it doesn't change, and then it starts to change. But I have manifold pressure resolution of 1/100th of an inch. And then you can see those things. And if you're at 17.5, 1/10th of an inch is a lot of power. It's a fair amount of power because you're already so low. But with the NACA duct, and you know, we know that at 17.5 is 50% density, so you should get 50% RAM, or 50% of the manifold pressure. And I've seen on a 30-inch day, I've seen 17.1 inches. Now that's a lot. You don't get that with a small intake. Yeah. And at high altitude, I don't need the huge throttle at sea level. If I was just going to EAA pancake breakfast, I wouldn't have that. But at 17.5, that large diameter makes a big difference. Just like with vacuum pumps, you know, vacuum pumps that pull down to microns of an inch. In the composite industry, they have giant hoses to it.
I think it's 16.7 at 15.5.
Well, 15.5 is a big difference. Yeah.
So not nearly as well.
Yeah. You need to compare it at 17.5. So that's about the NACA duct and the tuning of the engine. I made the new cowl now with high temperature epoxy, 305 degree cure temperature, two vacuum pumps, two industrial side, not the air conditioning pumps, but the real, $5,000 worth of pumps hanging on this, pulling this down to 5 microns within the absolute vacuum, and it made an incredible quality part.
Wood core or
No,
honeycomb?
that's a really good question. What kind of core did I use on that? And I've learned the hard way that we shouldn't use any cores on the cowlings. And the reason is composites develop micro cracks over time. There are voids in the composites. If you do a hand layup, the best you can do is 5 or 6% voids. If you do a vacuum bag layup, you can get down to 1 to 2% points voids. If you do an autoclave process, you can get down to like 0.1% or so, 0.4% voids. That's what autoclaving in the aerospace industry is all about. So what happens is you have these voids, little air bubbles in there next to the weave and the epoxy, and they don't affect the structure very much, but as you exercise the laminate, micro cracks emanate from there, and they get longer and longer, and eventually they go through the surface, to the surface. So if you have a core, you have a very thin laminate which won't seal the core, and then you have migration of oil and dirt into that core. If you ever take a core, old cowling, and cut it open, there'll be oil and brake fluid dirt coming out of it. So it's hard to get the panel stiffness without a core. If you want to have a lightweight cowl, it's hard to do it without a core. And that's why I went to this high temperature cure epoxy that is much better than normal, and the ultra high vacuum pressure. So no, there's no hollow. It's just the three or four layers of carbon.
What's the gloss transition temperature of the high temp epoxy?
350, 360,
Fahrenheit.
super high.
Yeah.
It's as high as it gets. Yeah. In epoxies, you have to go to thermoplastics to get higher.
Yeah.
So it's very, very high.
Is it common and can you get it easily?
In large quantities, 5-gallon pails. Yeah. I had too much of it. I gave a bunch to Gregory at Composites, and he will never use it all. I think I gave him 2 5-gallon pails, and you can get some from him, and then you buy the 826 or 828 standard resin to mix with that.
Thank you.
But you do need an oven that gets the temperature.
Kitchen oven work if your part's small enough, right?
I'm sorry?
The kitchen oven will work if your part's small enough.
If you can control it properly, yeah. Kitchen ovens.
Do you have pictures of your build on that? 'Cause I'd love to.
I do, but I wouldn't know where to find them. I need to organize my pictures sometime. So the other pet peeve of mine is data acquisition, and like the crankcase pressure is really helpful. It's the first thing. If you're about to have an engine failure, the crankcase pressure is the key. So I have it hooked up with red flags and alarm if it goes above a certain point. Like I said, at first I throttle back. If that doesn't change anything for a while, I'm going to look for a place to land before I have a hole in my piston. So fortunately that has never happened, but I want to be alarmed before it does. So
PSI. What's your alarm set at?
about 0.5 kilopascals. You can convert that. It's, I don't know, 0.2. It's about 150, 180 miles per hour worth of dynamic pressure. So, but there are other things. The other thing is vibration. I'm now flying. Well, let me start over. When we balance the propeller, a propeller that has an aerodynamic imbalance, you can mass balance it, but if it has an aerodynamic imbalance, if one of the blades is different from the other, you cannot balance that out on the ground. It's impossible. So the only way to balance it, and the aerodynamic imbalance, you can only balance out with mass by balancing it at that 1 RPM, or very close to it. So in other words, the only way to balance a propeller is in the air. So I have my vibration sensor installed permanently. And quite frequently, I just go fly with it. The wires are in the front, plug in the balancer, and check it out. Do a little readjustment if I have a prop nick or something. And so that's very helpful. But I'm working on getting the balance information, just the inches per second on the Garmin. And I have it all hooked up, but the sensor that I bought isn't working. I need to send it back. Well, no, it's supposed to be compatible, but the manufacturer said, send it back, we have to check it out. But so I was very close to having that here, but again, that needs to be alarmed. That's another one of those things. If you have a cracked crankshaft or a cracked case, or a bearing starting to go out, that will show in the vibration spectrum. And if you have that information and you're noticing that it's getting worse and worse and worse, you know it may be time to quit. So my objective, of course, is to not have the situation like several people had in the Wausau race. It was like a demolition derby this year. And we had so many engine failures and magneto failures and on and on and on. So, but they just happy-go-lucky go full throttle, and they double the horsepower on the engine, and oh, it broke. Okay, now I'm gonna land. Fortunately, yeah. Fortunately, nobody got hurt. So.
Now, when you were talking about the static balancing and then dynamic balancing, you're adjusting your dynamic balance, your aerodynamic balancing with weight, or are you actually changing the propeller to adjust for that aerodynamic differences?
Good question. We have static imbalance and aerodynamic imbalance. And the question is, do I do the aerodynamic balancing first? I don't know how to do that because I don't know where the imbalance of the propeller comes from. It could be a small, a minor leading edge change. You know, and it's not obvious, so you can't
just start from scratch and go, I'm going to try this.
Yeah, no, that's hopeless. So you can take the balancer only and mass balance the aerodynamic imbalance out at 1 RPM. And do that at your cruise RPM or whatever. Yeah.
Could you put that accelerometer parallel to the crank? Figure out which blade is pulsing, like doing a rotor again?
The question is, how do I mount the accelerometer? The accelerometer is always perpendicular to the axis of the crankshaft on these engines. But if you want to learn about balancing, talk to DPX or Matt.
One blade's pulling more than the other. If you put
Well,
parallel, would you feel that pulse greater push on one side or the other?
if I wanted to, I could maybe work hard enough to find out which blade it is. But it doesn't help me because I cannot change the aerodynamic shape of the propeller. I don't know accurately enough what it, you know, there was a story once where there was on the U2, the U2 at very high altitude is in what we call a coffin corner. It has only like 5 knots or so between stall and Mach over speed. And that one airplane had only 2 knots. It was impossible to fly because it always wanted to stall one wing. And they measured and messed with the wing, and eventually they got somebody outside to look at it, and he said, oh yeah, look, the leading edge radius on this tip is a little different. But they had worked for a couple of years trying to figure out why this airplane was messed up. So it's very hard to do that.
Well, the technology of the 3D scanners and all, do you think that might help us evaluate or assess? Because the technology is incredible nowadays.
Do you have one? Do you have a scanner?
Crap, I left it at home.
Yeah.
No, but
Okay.
But I'm wondering if you're thinking that
Yeah,
might be something that in the future we'll be able to leverage.
In the future, I'm probably dead.
Hopefully not, sir.
But the problem with scanners is that it's easy to scan, and the scanners are down to, I don't know, $3,000, $5,000, $6,000, affordable for some. And then you have a scanned thing, and then what do you do with it? You have a cloud of numbers, and it takes a couple hundred engineering hours to make that into a solid model. So you can't really do anything with the scanning. So this, by the way, is my very best propeller that I've ever made. And due to the very high torque and the light that I have on the engine and the lightweight, I've been able to take this off in less than 300 feet.
What are
So, and rotation would be like 1900. As I said on the forum, RPM doesn't matter at all for takeoff on the prop. It's a thrust. It's how much thrust you have. That's what takes you off. It's not RPM. So yeah.
Something related to the aerodynamic effects on balance came up on one of the most recent times I was copying you, and I was changing the lower cowling contour, and I was amazed how much change that made my prop go rough in the air, and I had to balance to compensate that with air obtained data.
Yeah.
I was surprised at that.
Yeah, yeah. Well, I noticed with a new wing that I've been test flying, it has a large cusp in the back, on the under camber in the back. It's pretty significant, and especially at certain speeds and at certain forward speeds and angle of attack, the propeller is really rough. And that's because the inflow into the propeller is now at a worse angle.
Okay.
And I'm going, maybe that's why Bert pulled that edge up. But I don't think he was that smart.
Yeah.
I think that was done because of the cowling. But this, from a propeller vibration standpoint, is actually a good idea to decamber the airfoil right here.
Okay.
As he did. For landing, it's not so good. There was another question, I thought. No? All right. The rudder, I had a similar rudder on the new wing, you know, high aspect ratio rudder, going almost to the top, but I also canted the wings out, and that made it really, I cannot side slip the airplane, made it really bad. So I lowered the rudder, shortened it, and that made it a little bit better. So Bert was spot on when he made that ugly board on the original Long Easy, because it doesn't cause the adverse roll that this kind of rudder causes. So if I was to do it again, I would bring it down at least 2/3 and maybe another inch or two forward. You know, reduce the aspect ratio so it becomes more of a drag board than a flap. This is a flap, and that produces lift, and that lift vector, being 90 degrees to the surface, is above the CG, and that rolls the airplane. So you have adverse roll, and you can't overpower that with your aileron at low speed, so you can't side slip at low speed. So yeah.
On your propeller, are you taking advantage of the thrust pulses with that extension where the trailing edge is going out? Is the engine producing more thrust at that point on the propeller? Is that why you have that?
Good point. Question about the extension of the propeller near the root, and if I'm using it to, let's go over to the propeller, take a closer look at that. So the velocity, of course, increases from root to tip. Here the velocity is 0, and here the velocity, you don't want to see the tip velocity above Mach 0.8, and that's the limiting factor on the diameter, besides the ground clearance. But of course you have acceleration above the thickness, above the over the airfoil. You have acceleration, so with a bit of sweep you can get to Mach 0.83 or so without too much of a drag penalty. But if you make the tip really short, then the Mach number drag rise isn't so great because it's proportionate to the area. So if you have a wide chord tip, then you run against the Mach limit, it's really bad. But if you really have a really small tip, it's not bad at all. You still have a speed increase when you go transonic. But the forward speed of the airplane defines the angular change between here and here. And you notice, especially if you look at this propeller, 90 degrees to this surface, and then look at that, you can get a feel for the overall pitch. And there are very few propellers made these days that have that much twist, that have the right twist. And one of the propellers that is twisted correctly is on the Risen airplane, which is on the west side of Exhibit Hall C, and that's a 230 knot light sport. Okay, they did a lot of things right on that airplane. It's worth looking at. The propeller is one of them. Really, really nice propeller. So, because nobody could make a propeller with the proper helix angle for me, I did that myself. But still, the velocity in the center is so low that you know, you want, like on a wing, you want aspect ratio. And the effective aspect ratio is if you have an elliptical, the maximum effective aspect ratio is if you have an elliptical lift distribution. So you can't get that with a propeller because the velocity goes to near zero here and it is at zero here. So you can increase it, you can spread that aspect ratio this way, or the span-wise efficiency, by increasing the angle of attack a little and increasing the chord. So that's why there's a chord extension here. And of course, beyond a certain point, it should look like this, but you know, or like this. And you know, it gets to be silly. You know, it doesn't do very much. But if this is at a high angle of attack, or the right angle of attack per the helix theory, then you also have maximum outflow here. And you know, I see a lot of propeller, like on, if you look at the propeller on Joe Coraggio's airplane, the 3-bladed propeller, it has half the twist distribution. So the airplane goes about half the speed, oh, almost. But if you look at it, it's flat here. So you'll inherently have cooling problems, you know, it restricts the outflow. But if you look at the exhaust plume here, you can see it better on the other side. But you notice that the exhaust plume is more or less parallel. And that means that the exhaust hits it, that the propeller is at the right angle. If it's flat, you have the exhaust plume splay on the blade. So it's a good indication that that angle of attack is about right. So,
what about your exhaust there? I see you've got different lengths. Is that from one side to the other? Is it?
Well, the cylinders are in different positions, so the length has to change.
Okay, so those are exactly the same on both sides then, or is it not?
They can't be the same length because the number 3 cylinder is further forward. So, and I've played a lot with the intake tuning. I haven't played with the exhaust tuning yet because there's just not enough room to do much. I have some ideas on something to do on that, but haven't I haven't exercised that yet. It's just I'm too busy with the wing right now. So, but you do notice that the exhaust pipes, I mentioned that last year, the exhaust pipes are separated. They do talk to each other. There is gas going from here into there and from there to here. If, you know, the closer they're together, the more communication there is, and that's not a good thing. So the other thing, you notice how crooked that cowling is? There's a little reflex here, and this surface comes up quite a bit, and that is for the inflow into the propeller. So it's like a stator blade, and subsequently on the other side, it comes down here a little more. This warped a little bit, and that's why there's this insert here to help have the air come down. So so the propeller can use that that outflow a little bit better to generate a little thrust out of that. Last year or a couple years ago, I made this outlet, and that really helped. So I thought, maybe I'll put one on the other side too, and that made it worse. So this is, like I said, the new cowling, and so I put it only on this side, and this seems to be the side that has more attachment, and the outflows. This is a really good exit. I really like it. So all the other stuff already talked about last year, and let's see if we have any more questions.
Gap with the cowl right there, is that a reason?
Well, no, that's actually a good observation. That gap in the cowling, it's not for a good reason. The flow here, all the flow measurements show that towards here there is still a substantial amount of span inward flow. And on the previous cowl, I had lowered this about 3/4 of an inch and made it square. And on the new cowl, I did away with that because it didn't seem to do anything except add weight. So I made this cowling kind of fit this. This is not an air leak because the seal is here. The seal is in front of it. So it's not as if there was air leaking out of that at a substantial rate. But I made this new cowl last year or earlier this year, and the next step is to make a mold off of this and make a new cowl for the top. Once I have the new top cowl, then I'll worry about making that better looking. So, any more questions?
I mean, is there a reason this is asymmetrical?
Yeah, I kind of eyeballed that, and you can see that you see that the outlet is high here and low here. That's why I did that, so the outflow could be a little more uniform there.
It's uniform through this section, but not.
Yeah, I mean, I need to twist the flow. This flow needs to go up into the blade, and this flow needs to go down into the blade. So I wanted to have a little more exit area on this side to help with the cooling. But that's not, none of this is calculated,
Okay.
or a lot of that is eyeball engineering. So
Your wing with the cusp you were talking about earlier, did you start that on CFD work or just?
I don't do any computer work. I'm more or less computer illiterate. And I tried to get into computers a long time ago, and it takes me more time to sit there and think about things than build things. I just lose time to build things. It takes too much time to actually make stuff happen. So I've given up on that. Sometimes, like on the new wings, the blended winglets, they have to be CNC machined. We had to do a computer model on that. It's impossible. There's a twist change, a sweep change, a thickness change, a camber change in that blend that I wanted, and that's absolutely impossible to do that with hand jigging. So it had to be CNC machined. And
you're building something and then you're just oil flow testing that.
yeah, lots of oil flow testing, tough testing, yeah. And like I did these, well, this is the old canard, and I did these Dornier tips to basically twist them so that there's not a tip vortex at all. So that the very tip tapers out to be at zero angle of attack in cruise. Of course, you have lift and a vortex at high angle of attack and climb. But the idea to get it to zero vorticity at cruise. And I guessed at 6 degrees or something, and that wasn't nearly enough. So then I cut it horizontally and twisted it to 10 degrees, or actually I went to 8 degrees first, and that wasn't enough. Then I went to 10 degrees and just glued it back together, and that's why those tips are so messed up. I never got to finish it. So for the new wing, I now built a new canard, and on the new canard, I hot wired it properly. Now that I knew what the zero lift angle twist was, I hot wired that, and it's precise, and I'm going to a symmetrical airfoil also. This is still a cambered airfoil, so to have that, you know, the new canard is really nice. I've flown it already. It still has a little bit of, well, the new canard is made for the new wing, so it can't fly right. I can fly it with this wing, but it won't be perfect.
Do you have a name for that new canard? A name for the airplane? You've got the delaminator, this one, and then...
Well, I have the delaminator and now the determinator, and when I put the new wings on, it's going to be called Adrenalina.
Which is?
That's just the name.
Sounds like a beautiful woman.
Sounds like a scary woman. So.
Are you gonna do the wings out of any kind of a different material?
Yeah, the new wing. Well, I've been working on the wings for 24 years, and I have flown them. So, and they are made out of S-glass, largely. All the spanwise laminates are S-glass, and the torsional layer is out of carbon, except for the winglets, because there are antennas in the winglets. So it should be a super strong wing, and I had it to 4Gs so far, and I don't see any cracks in the primer. So
See it at Oshkosh next year?
I hope so. I almost brought it this year. It was really close. It just the problem appears to be that the drag, the parasitic drag of the wing, is now so low that it affects the stability of the airplane. Because the CG is at the more or less at the belly button of the passenger. So the entire wing and strake, most of the strake, wing, winglet, everything is behind the CG. And that's like adding a feather to the back of your arrow. It adds directional stability, or stability in all directions. And if you take that stability away, it's like trying to fly an arrow without the feathers. And that's something I didn't anticipate. That's and I also noticed, the original winglet design was made for absolute minimum drag. The whole wing was designed for absolutely minimizing the drag. And I learned that the winglet design on biz jets and airliners, they're not for stability. They're only there to deal with the vortex. And it turns out that those are two totally different animals. A winglet on a canard for stability is a different animal. And I know only 3 people in the world that have a faint clue about that. And you're nodding, maybe you know too, maybe you're the 4th person, but
I know it's different.
Yeah.
I'm no expert,
you sometimes you hear that they're different, but nobody can really put their finger on what they're doing differently. But you can recognize the fact that they are different by the airliners and biz jets never reducing the vertical. If they were gaining yaw stability from the winglets, they would be able to reduce the height of the vertical and save drag, right? But they're never doing that. And nobody says the 737 MAX with all the winglets hanging out there are more stable, directionally stable than without. They're not. So those are two totally different cans of worms, and I have to do something to build in aerodynamic stability without adding drag.
What is the effect of the lack of aerodynamic stability? Like if you were to fly it, what would it feel like? What would it be?
It feels like you're not in charge.
What's that?
It feels like you're not in charge.
Okay, but it wants to always do something different.
Yeah. Unstable.
It's not a CG problem where you're worried about being out of CG.
It acts a little bit like a CG issue. It tends to PIO. But adding weight in the nose doesn't fix it.
Oh. Huh.
With lengthening the distance between the canard and the wing is help.
I think the question is, would the distance, the décalage, basically make a difference by changing the distance between the canard and the main wing? I did anticipate a little bit of that, so we had put more sweep in it too. So that brings part of the wing a little bit further back. It's a little bit too much work for me to cut this thing in half and add a foot in the middle. Jenny would appreciate the extra space, but it's just a little too much work, so that's not on the table.
You gotta get it safe,
But-
so get it safe.
But also, I don't think that would be helpful, because you're destabilizing the airplane further by moving the canard further away from the CG. Canards are just inherently unstable. They're a mess. It's really complicated, and I don't have a full grip on it, I must admit. And I'm not sure. Bert, well, he probably does, but he can't explain it to me.
What about moving your winglets, mounting the winglets further back on the wing, on the edge of the wings?
The question is, would mounting the winglets further back, that would help. That would help. It's just a little too much work.
Okay.
That's a lot to
It's
change.
yeah, that's not for me, I don't think. So, but I did increase the camber on the winglets by a lot, by about 30%, and that helped a lot. So it's kind of flyable now, but not ready for prime time. So. Anything else? Yeah.
What pressure difference would the vet here versus there? Do you have any idea?
This is high pressure.
Yeah, so I mean, we still got a lot of us still have been right up in here, right, just inside.
Yeah.
So,
well,
get it.
You know, the trailing edge always has high pressure, so you'll never get to low pressure there.
Right past.
This is
Right past the thickness, the maximum thickness is just starting to get low right there.
Yeah. Well, this is outside of the boundary layer. You need to get outside of the boundary layer.
Like I've got your original cow. Is this for spark plug? There's a little bit of, or is it just on top?
That's on top.
On top only.
On the O200, right? You're talking about the O200 cow? Yeah, that was on top.
Yeah, only.
This is all different here.
Now I'm looking for a better place to put it. That's what.
Yeah, no. The best thing is to make a little fairing to get out of the boundary layer, and your boundary layer is probably a little thicker, and angle it down at 30 degrees to the airflow. That's the number.
And the little fin on top of the cowling up there.
Yeah, that's just like a stator blade. It doesn't make much difference, but it just helps. Due to the rotation of the propeller, the inflow rotates also. The whole air column going into the propeller is twisting, right? And the straighter you can make that, this helps as a fin to straighten it out. So thought I'd straighten it out here too. Ideally, this would be the same diameter as the propeller, like a stator blade in a jet engine. So it does seem to make a little bit of difference in climb. not sure if it's helping in cruise, but it seems to help it climb a little bit. Yeah.
Would taking that to help solve your aerodynamic instability with the new wing? What if you
Make it
adding
bigger?
more, making
Well,
a full-on strake above or below?
yeah.
Or at the
Remember,
trailing edge of the wing?
remember that would primarily increase drag.
Yeah.
And I'm trying to avoid adding drag.
Okay.
I can put vortex generators on the wing, and I think it'll work just fine.
Yeah. But that's drag.
Yeah. So, but
How much faster is your new wing? Do you think it's going to be than this one?
well, the parasitic drag of the wing is almost half of this wing, so you can calculate it from there.
Oh, we'll see next year.
Yeah. Make it easy. Yeah. Yeah.
Why not mount your engine breather to the exhaust like we see all the other long easies do?
Yeah. Why don't I extract it from the exhaust? It's heavier to do it that way, and there was 30-some years ago, there was a good friend, the late Wes Gardner. He came out of boat racing, and he came out with a kit, an extractor kit, to put the exhaust, to extract the breather through it with the exhaust. And he had an anti-backflow valve and the plumbing, and he made a nice little kit. And we were really good friends. And he said, Klaus, you got to try this. You got to put this on your O200. And I said, thank you, but no thank you. And he went on and to Mojave and talked to our friend Dick Rutan. And he gave him one, says, please put it on, and he did, and it was fine. And a couple months later, it was time to go to Oshkosh. And the story was Dick filled up his airplane with fuel and oil, took off, and he landed in California City without oil. It's about, I don't know, 50 miles, not even 30 miles. So he pumped all his oil overboard. So if that isn't plumbed right, and the anti-backflow valve hangs up, you can suck your oil out of the crankcase overboard. So he then took that out and never did that again either. So I don't want to shoot myself in the foot. This works beautifully. I get slightly negative pressure, and by the way, that negative pressure is responsible for ring seating. So if you have high crankcase pressure, your rings will never seat.
Do you need the separator?
No, I
If you're
don't
not
think
doing
so.
manufacturing, if you're just
I don't
flying,
think
you
so.
wouldn't need it.
I don't
You
think so.
wouldn't pull an oil out.
Yeah, yeah. And I'm not sure how effective the separator is. You can see, you can see that line of oil, and it comes here, and then it travels on the trailing edge because there's a stagnation point here. Then it runs down here somewhere.
Yep.
And so this flow is really good here. So I'm sorry.
You don't have any sump blisters. You do a header tank like the very easy.
Yeah, I talked about that last year. That was one of my better innovations, the fuel system, and I took away the sump blisters because the sump blisters aerodynamically are in a really bad place because they blow air out of the way at the same fuselage station as the gear legs. So there's this double velocity increase there, and that's fairly draggy. So that was unacceptable. I don't like the sump underneath the passenger's thighs. That's kind of bad in a crash. And so I put a header tank in behind the headrest of the passenger. But with the long easy strakes, they're big enough so you can't fill it at the gas pump. You can't really reach there without climbing into the back seat. So I'm too lazy for that too. So I put a little 5 psi pump in the hellhole, and the pump fills the header tank from the left main tank. And there have been numerous airplanes crashing due to transfer pumps that were left on too long, because you overfill a tank and it goes out the breather and you lose fuel, you have no control over it, you don't know it. And so I put a standpipe in there so that when the header tank is full and I leave the pump on, it falls back into the same tank. So I don't need to measure it. And so I can leave it on, which I always do, you know, for hours, and oh, I forgot that, yeah, no problem. But I have that standpipe that saves my bacon. And so that's a really, really good system. I really like that. I have, you know, the strakes are made for those are new strakes that I put on about 5 years ago. They fit the new wings. That's why there's this discontinuity on the leading edge. And they ended up at a much higher angle of attack on purpose. And with the high angle of attack, I don't even need sumps. You know, I have zero unusable fuel, and it takes a substantial nose down to unport at low fuel quantity, very substantial. So, but the header tank that's my Jesus tank, and it's always full. And there's an anti-backflow valve in the pump, and there's an anti-backflow valve in line in addition to that, so it doesn't come back to the pump. But if I did it again, I would use the fill line to go to the top of the tank, so I wouldn't need that anti-backflow valve.
Yes. Afterwards, talk to me about mine. Afterwards, talk to me about mine.
Okay, all right. So, yeah, so the fuel system, the way I have it rigged, I don't even look at the fuel tanks with any accuracy. I just see, oh, there's more than half an hour of fuel on board. And then I have my Garmin set up to wake me up every 30 minutes to make a tank change. So every half an hour I go back and forth. And if one of them quits, I know it's empty. At that point, I look at the other one to see how much I have, make a decision, and then I run both. I can run both main tanks empty, and then go to the header, and I have a known quantity of 2.2 gallons if it's full, and that's plenty to get to the ground even from 17.5 and still have power. So I love that fuel system. I feel so safe with it because I don't have to think about it. I don't have to worry about it, and it's just, oh, it's great. So, well, I know it's a lot of work, but man, is it worth it? You know, it's yeah, yeah. And the other thing I would do different, I don't like the long 3/8 lines spanning the whole fuselage for two reasons. One, it's generally not a good practice to have fuel lines in the cockpit. If there's a bad impact, you know, they might tear loose and douse the passenger people with fuel. The other reason is if you do run the fuel tank dry, it may take a long time before you pump the air back out of before you replace the air with fuel. And if that happens to you at 300, 500 feet up, you're not going to get the engine restarted. And that's a bad thing. On mine, it's a little bit better because, well, my technique, if that happens, is this. I switch to the header tank because the header tank is higher up, so it has more pressure. And the other thing you want to do is go to full rich and full throttle so that your servo or whatever fuel system you have demands maximum fuel flow. because that replaces your air in the lines faster. So that's an important thing to remember. If you ever run the tank dry and you're down low, go to full rich, and then as soon as it starts, you bring everything back to where you want it to be. Anything else?
Do you have a preferred method for defining the areas that have laminar flow and where the transition is to turbulent? And have you tried smoke for that? Just flying through smoke?
Well, that was my technique. I showed you pictures of flying through smoke. I can tell how far the laminar flow extends, but it has to be pretty heavy smoke, and it has to be. It might have to do with the polishing compound that I use. The last time we had this big fire in San Ynez, I flew through the smoke for like 45 minutes and nothing really deposited, so I couldn't tell. So the smoke is really helpful. Back in the days, Bruce Holmes, who worked with Bert Rutan a lot on laminar flow, he used, and I remember, I may be totally wrong, but I remember mothballs dissolved in naphtha.
Oh.
And they brushed that on, and that left a film that would indicate the change from laminar flow to turbulent flow.
Was that the sublimating fluid?
Sublimating, that's what they call it, sublimating chemical.
Oh.
But it turned out, I remember it was mothballs dissolved in naphtha.
Okay.
I may be wrong, but it's been so long. But I was gonna find one of those old timers and say, hey, yo, you know. But they called it something really fancy, but that's all it was.
That's what Bert had in the newsletter, sublimating chemicals.
Yeah, yeah. Make it really mysterious.
Yeah.
But
That just collects the smoke particles and you can see where they're.
I have not worked with that, those sublimating chemicals, but in the past I've had great luck with flying through heavy smoke. So that's, in case you wondered why we have so many fires in California.
Allows us flight testing.
Just by airflow.
Just flying through it, it'll collect, or do you have to put anything on the wing?
No, but it has to be perfectly polished, so that the particles in laminar flow do not stick, but after the turbulent transition, they impact the surface hard enough to stick, and you see like a gray shine, and you have to look at it when the sun is low at a really shallow angle. You can see it. If you want to email me about flow pictures, I can send you some flow picture. You can show you what it looks like. It's really hard to see. I've never been able to get the bottom surface to the right angle against the sun to see it on the bottom, but I saw pictures on the main wing and on the winglets and on the canard. And if you remember, a couple of years ago there were these huge fires at the Reno air races, and one of the guys came over, running over, and said, hey, come over, look at the legacy, look at the legacy. And sure enough, they had the same thing just from racing around, and we could clearly see where the transition was on the legacy wing. It was very interesting.
It's totally accidental. I flew through some smoke and got down and I did a double take. What is it? Mainly on my winglets. And you could see where I'd have a bug and the transition underneath that.
Yeah.
And then there's a line where most of it was all transition
right. You get
beyond
that wedge,
yeah.
7-degree wedge.
Right.
Or this way, and then flat line, yeah.
Really interesting.
Yeah, did you measure how far back it was?
No, I took pictures. I've got them somewhere.
Yeah. What I did with mine, I took a Sharpie or one of those racing things, and I look at it and I mark it, and then I measure it. It's good to know how far that is.
Yeah.
And these are the only wings that the only wheel pans that have the attach line way behind the transition point, because on this airfoil, on this wheel pan change, the transition is actually behind, well behind, about 3-4 inches behind the split line. So that's why I moved that back. Anything else? I think we can call it quits now. Yeah.
Do you have a custom camshaft? You're talking about valve overlap?
I do not. I do not. The I don't find anybody that I can communicate with on that level. There all seem to be some hot rodders that have some wild ideas but don't really seem to understand the science with all that.
Will Kenny talk? He supplied my engine with a performance profile. I don't know what that is.
Yeah, well, measure it. Measure it and then we'll compare it.
Okay.
It's easy enough to measure. I don't know. It doesn't seem, I don't think you can make any progress with a camshaft change with a normal injection system or a normal carburetor. But if you have fuel injection, and if your injectors are such, if it's timed sequential, meaning that the injector period coincides with the valve opening, and if the injector size is big enough to only inject during that injector period, so you don't spray into the intake manifold while the valve is closed, then you can maybe have more valve overlap. If you increase the valve overlap and you're pumping fuel into the intake manifold when the valve is not opening, then you're becoming very inefficient. So when Kenny does something, he does not care one bit how much fuel you're going to be burning. So, and he doesn't even look at that, you know, horsepower versus fuel flow, the whole brake specifics, you know. I'm all towards 0.4 pounds per horsepower per hour or better. But a lot of those guys like Ron Munson and Kenny, they go, oh, look, I get that engine burns 20 gallons an hour. That's 250 horsepower, you know. So like I said, I can't communicate with people like that because it's not on. Doesn't work.
Lean to peak it would be, right? If you're lean to peak, then
if you were doing well, you
same compression ratio.
If you were doing it with a lambda sensor and you go to the same fuel flow, to the same air-fuel ratio, then that would help. But the goal is to improve the efficiency of the engine. And so the peak EGT has nothing to do with compression ratio and flame front propagation speed, or for example, ignition quality. You know, the ignition quality is not really reflected in that. As a matter of fact, and again, some of these cowboys, they think the higher the EGT, the more horsepower there is. Yes, there is, but it may also be that the flame is too slow and you have more burning in the exhaust. So if you can't differentiate that, you're not making progress. So it gets very complicated there.
Your primary power indicator is how much pressure is in that cylinder when it's coming back down.
It's the BMEP.
Yeah.
It's no, it's the torque really.
Yeah.
And like, you know, Garmin gives you percent power. Well, they have no idea what the percent power is. The only way to measure percent power is to have a torque meter on the engine. So I can go to peak power, peak power, level flight, peak power mixture, peak power timing, and it tells me that I'm at 60% power at some altitude, okay? And then I go way lean of peak and advance my timing to get that back right. And I lose only 5 miles an hour, but it tells me I'm at 45% power. That's how far off the Garmin percent power indication is. So you can, percent power you can only really discern with the torque meter. It's the only way to do it. So.
Sounds like a future projects.
Yeah, if I live long enough. Yeah, it's actually on the radial engines in the 50s and 60s. They had a torque meter built into the gear reduction.
Off the ring gear.
I don't remember exactly how they did it, but it was a hydraulic device that was changing pressure with torque from the gear reduction that they could read in the cockpit.
The way they did it in Herc is they got a free shaft, a torque meter about that long with the free shaft on the outside and the spline shaft on the inside, and it would read how much deflection there was at the end, and they would time the difference in the teeth. That would tell us the torque.
On where is that?
On the C-130 engine.
Which engine?
KC-130 engine.
On the KC-130. KC-130. On the jet engine.
Yeah, the turboprop.
Turboprop.
So you got that shaft that's about yay long.
Okay.
The power section and the gearbox.
Yeah.
They
Yeah.
the how much deflection the shaft
Yeah.
have with the torque.
A rudimentary way could be built into the motor mounts.
Yeah, I was thinking about that.
Road cells on the motor mounts.
Yeah. All right. Answered all the questions. Brent?
I have no questions.
No battery questions?
No. Film that picture. I have a picture of my prop.
Oh no, you didn't damage your prop, did you?
No. It's fluid through smoke. Whoa. Just lost it.
If you guys look at Klaus's flights on FlightAware, you'll see he does much more research and testing than the rest of us. He's always doing test flights.
Yeah, there you go. There's a picture of the smoke, the wedge from the bugs.
Oh wow.
Pretty good for a prop.
Yeah.
Oh yeah, look at that.
It's like 3/4 of it's laminator.
Yeah.
And whose prop?
It's my
But I mean, manufacturer? Okay. Cool.
Yeah, very good. That's what it should look like on the wing too.
Unless it's my wing.
Yeah. Well, yours is that way, hopefully on the bottom.
Thanks, Klaus.
You're very welcome.
Thank you.
Thank you. Let me open the canopy. Open the canopy for those guys. Hey, Dave. Good morning. Good.
How's your morning?
All right. Not quite awake yet, but let me open the canopy. No, don't be sorry.
Who do you think you are moving each other?
Yeah.
Well, you're right here.
Please admire my wiring job.
What's that? Yeah. You've got so much visibility. I mean, we flew up and it's Bonanza, and I mean, obviously you can look at things, but he's got like the heat or the sun shading in it, but where he's got the cutout, you've got that clear, and you right there. I mean, that's got to be something at 18,000 feet when you're sitting there looking through that.
Well, the interesting thing is when I put in the windows, instantly the traffic around me doubled.
Oh. I'm going to ask you one question if you can give it up. what is the size of the opening of your NACA dome? Is it just kind of a standard opening, or did you size that?
I did all that development about 30 some years ago.
Yeah, because on mine, I am putting a NACA duck on that
So-
project of mine.
Yeah,
Because
absolutely.
I got the fixed gear, because I have that fixed gear in it.
It's definitely the
So-
best way to go.
Yeah, and I've started
And
to lay it out, and that's the only thing I haven't. They give you the dimensions.
you should
on it.
no, you should buy this NACA duct is modified from the original, and you should buy this NACA duct from Aero Composites.
And what do you get when you get that from them?
I get nothing.
No, but I mean, no, I'm not saying that, but what do you, as a person, get from them?
You get a carbon fiber duct that has a floor, a wall, and a flange.
Okay, and then you can go and modify that as it goes around the thing.
And it has the diffuser in the back that reaches into the 1 foot,
Okay,
1
all
foot
right.
radius. And they have my molds, and that's what I highly recommend getting that.
Well, then that's what I'm gonna
yeah,
do.
and get it
Composites.
Aero Composites.
That's where I got the gear. And stuff.
Gregory,
Yeah, I mean,
Aerodynamics. So
yeah, he's a pretty good guy.
Yeah.
That's good. Good
Yeah.
things.
So we're gonna put one more on you just in case.
All right.
I'm gonna stick that in there. We lost the clip on this one, so I'm improvising with a paper clip.
Your wiring looks like my hanger.
Yeah.
Does your hanger work?
Yes.
All right.
And I know where everything is.
How thick is the plastic?
The plastic?
Yeah.
Plexiglass?
It's pretty thin.
1/8 inch.
No, it's more than that.
So a quarter.
It's
So you
probably 3/16.
okay?
Because I had to router a flange
Right. Okay.
to get it flush.
Yes, and that's
But also this is a very structural area, so it's this unidirectional carbon all the way around.
and how far down did you take it to do that? Because you cut the hole out. Did you have to?
This is all I did. The bottom below that it's still original.
But see how you've got that recess in here. So you get the recess. How far does this come home this way to add into the structure? Up
I don't know, an inch,
inch.
inch or inch and a half.
I should do that. I should put those.
It
in
took
there.
me a week.
Yeah.
And then I had to have therapy for another week because my back was hurting so bad. Because you do all the work bending over.
Yeah. Right now, I didn't put the spar in the airplane so that I
Okay,
could
so you
roll
still
it
turn it.
all
Yeah.
around
Yeah.
to do all of the. major
Then it's
pieces.
easy.
Yeah, and that's
But
why I look at it.
I
right
did
now.
all that bending over. It was
I've got a rotisserie. I'll mount it, flip the whole thing, and I can stand up.
Yeah, that could be.
You
done.
made some big changes to your instrument panel since
No,
last
right
year.
now,
I'm sorry, what?
You made some big changes to your instrument panel since last year.
No?
I thought you had like a fuse box on the bottom right. No?
No.
So
Okay.
with
I was going
The only thing different is this unit,
well, it's a long
which is not
gear.
quite working yet.
Okay, what is that unit?
It's a dash.
Okay. I'm not actually familiar with the dash.
No,
Did you ever
no,
watch Formula One?
Yeah.
When they crash and they leave the car, they take the steering wheel with them, right? You ever noticed that?
Yeah.
Because all the data is in the steering wheel,
Yes.
and that's called a dash.
Okay.
This thing records 250 channels,
Okay.
and I can set it up so that gazillion pages,
Yeah.
gazillion alarms, and resets, and it also records everything.
And you get audio as well?
I can program it for that. Yeah.
Wow.
And it has vibration sensors and like I said, 250 channels, and some of the channels you can program to record at 200 hertz.
That's amazing.
And it has a six axis GPS in it at 200 hertz. Then when the driver crashes, you can see exactly what the motions were and what broke when, to have full analysis capability.
Yes, that's amazing.
And so I'm trying to bring that into the aviation field, but you've got to know your stuff to hook it up, and I haven't quite managed that yet.
You're gonna get a lot of phone calls with the customers.
Oh, I'm not gonna sell this. No, I'm not gonna sell this. I'm just gonna
Present the idea.
yeah.
You ready to start?
Yeah, I'm ready to start.
Hey, good morning, canard enthusiasts. We're going to kick it off, and I'd just like to ask that everybody, we just have one conversation. You know, if you want to have your side conversations, that's great, but kind of separate from the group.